morning, chemistry students. Hey, it's Monday, 5/11/2020. Hope you had a great weekend. Weather wasn't quite as nice, but sure is looking nice outside, just a little chilly. All right, what's on tap for today? Learning targets. I can determine the type of hybridization displayed in simple molecules. Hybridization. All right, so let's think about this. People have been doing this for a long time. Let's say you got a dog that's got just this nice curly tail that you just love, and you got another dog over here that's got the same sort of nice curly tail, and so you try to arrange that those two dogs get together, and they have puppies. And we get some puppies with some nice curly tails, and let's say you do that multiple generations. You take the nicest, curliest tails. You eventually form a new breed of dogs. Okay, you're trying to take the properties that you want. Unfortunately, in dog breeding, they've been so inbred that also genetic bad things have come along with the traits that we want. And a lot of purebred dogs, it's very unfortunate, have a lot of genetic problems. So if you want a healthy dog, a lot of times you're better off with a mutt. Cattle breeding. We have different breeds of cattle because we're trying to get the best genetic combo for what you're trying to do. All right. So think about hybridization as trying to take the best properties of two different things and mix them together to get something new. If I were looking at corn, let's say I've got a variety of corn that has big plump kernels, and then I've got another variety of corn that's very drought resistant, and I try to hybridize them to get a new strain of corn that is both drought resistant and gives big plump kernels. Okay, that's the concept of hybridization out there. Now we're going to talk about that in terms of atomic orbitals or molecular orbitals. And the basic idea is, let's think about combining orbitals of similar energy to form orbitals of equal energy. So to get our brains thinking about this, I want you to think about methane. The formula is CH4. Go ahead and draw a Lewis structure real quick. I'll wait for you. If you're not done yet, just pause the video. That's a structure we've drawn a few times over, so I hope that was real quick and easy for you. So we got a carbon and single bonds to 4 different hydrogen. Now, if you were to look at this, it would appear that there are 4 identical bonds to 4 hydrogens. And I think that's what we get from experimental evidence, that those bonds are all equivalent. But if you think back to what we learned about atoms and the electron structure, that is not necessarily obvious to you. Maybe you haven't thought about that. But the electron configuration for carbon, 1s2, 2s2, 2p2. It's got 4 valence electrons, and the way we would normally have drawn that out would have 2 electrons in an s orbital and 2 electrons, single electrons, in the 3p orbitals. And if I look at that orbital arrangement, that doesn't give me that at all. And then even if I think about, well, could I take one of these electrons and just slide it over and then I have 4 single electrons? At least with 4 single electrons, I have easier time imagining 4 bonds, 4 shared pairs. But shouldn't that electron in an s orbital somehow be different in energy or properties than those in p orbitals? I have no idea what I was drawing down here, so don't worry about that. It just doesn't seem, and shouldn't there be some difference between these? And experimental evidence says, no, these are all the same. So we got to think about it differently. Now, we got the Schrödinger wave equation, describes the wave properties of electrons. That's that stuff that came out with the s orbitals and the p orbitals and the different quantum numbers. But remember, mathematical equations can have more than one solution. If I have the equation x squared equals 25. Well, you know there's two solutions for that, right? Plus 5 and minus 5. If I have y equals 5x plus 3, there's an infinite number of solutions that are all along a line, right? That's the equation of a line. X squared plus y squared equals 4. That's going to graph as a circle, and we're going to have infinite number of points in that circle that would all fit that equation. So here's how I think about it, and this is probably not the most scientific way, but I think of hybridization as just being an alternate solution. And I think of what we learned back in the previous chapters about electron structure. That seems to be the solution that fits best to individual atoms. But when atoms form bonds, there's a different description. Okay? So one solution works better for atoms, one solution works better for molecules. The hybridization works better for molecules. So this is really breaking it down to some really kind of hokey solution. I'm not going to get into the deep reasoning of hybridization for lots of reasons. One of being I don't truly understand it very well, okay, being honest with you. But this is one of those things where for a beginning chemistry student, I think we can just try to look at the results. And so I'm going to go through the results. You know that most atoms gain, lose, or share electrons to get 8 valence electrons. And 8 valence electrons would fill up the valence energy level. It'd be an s sublevel or s orbital and 3p orbitals. Now, what I want you to do is think about what if we take that s orbital and 3p orbitals and we combine all together those 4 orbitals to make 4 equal orbitals. Okay, so instead of s and 3p, we're going to get 4 that are all the same. Now, if I combine 4 orbitals, I'm going to get 4 orbitals. So this is the hokey part that I'm not real comfortable with, but I talk about, here's our magic box of hybridization. So if I put 4 orbitals in, an s, a p, a p, a p, what I get out is 4 orbitals, but now instead of a s and 3 different p orbitals, I get out 4 identical orbitals, and they're all called sp3, sp, and then it's a superscript 3, hybrid orbitals. So where s was a spherical orbital and the p orbitals are those peanut-shaped, the sp3 orbitals have 2 lobes, but one of them is kind of, almost non-existent, and these 4 lobes are going to point, well, a lot like what we had in our molecular geometry. Those 4 lobes would want to point as far apart from each other as possible. Okay? They don't want to overlap with each other because they're regions of space containing electrons. Oh, okay. So our most common form of hybridization is going to be sp3 hybridization. But there's other examples. What if we only combined an s orbital and 2 p orbitals? Okay, so we put 3 orbitals in the box, out comes 3 orbitals. These were slightly different energy, these are all the same energy. There was an s orbital, a p orbital, a p orbital. Each of these orbitals has a little bit of character from s and a little bit of character from each of the p's. They're called sp2 hybrid orbitals. 3 orbitals in, 3 orbitals out. What if you only combined an s and a p? 2 orbitals in, 2 orbitals out. Slightly different energy, equal energy, sp hybrid orbitals. What if we needed 5 orbitals? Well, then we go with s, p, 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 d. See, I always start with s, because that's the lowest energy orbital, and then I can have up to 3 p orbitals, and if I need more orbitals than that, I'm going to have to go to the d subshell. These are going to fit a couple of those exceptions that we had, like sulfur hexafluoride and phosphorus pentafluoride. So if I have S, 3 p's and a d, that's 5 orbitals. We get out 5 orbitals. What's the hybridization? sp3d. It's got character from each of those. What if I put in 6 orbitals? An s, 3 p's, 2 d's. Well, then I get out 6 orbitals of equal energy, and they're called sp3d2. So how do we know how many of these hybrid orbitals we need? We're going to look at our Lewis structure. Here it comes again. We always need our Lewis structure. And you're going to want to write down this list and study this list. We need a hybrid orbital for each unshared pair on an atom, for each single bond on an atom, and then when it comes to double bonds, in a double bond, what happens is we get one sigma bond and we get one pi bond. Okay? I should have built some models for this. I'm going to pause the video for a second. All right, let me see if I can pick that up. So, if we're going to make a double bond, first of all, let's imagine that each of the atoms has a hybrid orbital that comes together and overlaps to make a sigma bond. Okay? A sigma bond, remember, is an end-to-end overlap. So we're going to make a sigma bond, and I'm going to take that now and replace it just with a stick representing that sigma bond. Okay? Now, where does the second of the double bond come in? Well, here's our sigma bond. Now let's imagine we have an unhybridized p orbital that's oriented perpendicular. And here's another unhybridized p orbital, and those two p orbitals come together and overlap side to side to make a pi bond. Now, if you have to go back to our molecular orbitals lesson, go and do that. But in a double bond, you have a sigma bond of hybrid orbitals, and then you have a pi bond involving non-hybrid orbitals. With a triple bond, that's also going to be the case. You're going to have one sigma bond, and then you're going to have a pi bond, and then imagine we had another set of orbitals going perpendicular this way that are making a second or a third pi bond. Okay? So in the case of double and triple bonds, there's always one sigma bond and one or more pi bonds. We only need the hybrid orbital for the sigma bond. So all right, let's simplify it. For every double or triple bond, we need just one hybrid orbital. The others are going to be non-hybrid. All right, so one more time. On an atom, we got to count how many unshared pairs, how many single bonds, and how many double or triple bonds. We're going to need a hybrid orbital for each of those. So when I look at methane, on the carbon, I need 1, 2, 3, 4 orbitals, 4 single bonds. So 4 orbitals, I'm going to start with S, P, P, P. 4 orbitals in, I get 4 orbitals out. What's their character? They're sp3 hybrid orbitals. Let's try a couple. Okay, what's the hybridization of the oxygen in water? So, take water, we draw out a Lewis structure. Start with a Lewis structure. On the Lewis structure in water, the oxygen has 2 unshared pairs and 2 single bonds. I need a hybrid orbital for each unshared pair and for each single bond. That's 4 hybrid orbitals. So with 4 orbitals, I'm going to need an S, P, P, P. That's sp3 hybrid orbitals. The hybridization of the oxygen is sp3. How about BeF2? Now, when you see BeF2, that's got to be on our little mental radar as one of our exceptions. It does not, the beryllium does not have an octet. So beryllium just has 2 single bonds on it. So 2 single bonds, I'm going to need to combine an s orbital and a p orbital, right? We always start with s, and I only need 2 orbitals, so s and p is sp hybrid orbitals. The hybridization for BeF2 is sp hybridization. Let's look at SF6. Sulfur has 6 single bonds. It needs 6 orbitals. So I start out with the S, P, P, P. I'm out of p orbitals. So then I go to D, D. I've got 6 orbitals. S, P3, D2. Here, let's look at a carbonate ion. CO3 with a 2 minus. Count up electrons. Carbon has 4, each oxygen has 6. There's 2 extra, it's 24 electrons. They want 32, we've got to have 4 bonds. When you draw that out, you're going to have a double bond. Okay, so now if I'm looking at the hybridization of the carbon, I've got single bond, double bond. Here's where we got to remember, for the double bond, I only need 1 hybrid orbital. The other part of the double bond is going to be a non-hybridized p orbital. So I need 1, 2, 3 hybrid orbitals. So that's spp, sp2 hybridization. That carbon has sp2 hybridization. We could take this further and look beyond the central atom and say, well, what's the hybridization of that oxygen there with the double bond? Well, it's got unshared pair, and it needs a hybrid orbital for 1 part of the double bond. So it needs 3 hybrid orbitals, spp, sp2 hybridization. The other oxygens, we need orbital for each unshared pair, and for the single bond, that's 4 of them. So spp, sp3 hybridization. Here's HNO. Draw a Lewis structure, nitrogen's in the middle, single bond to hydrogen, double bond to oxygen, unshared pair. So in here I'm just trying to point out that on that double bond, 1 part would be sigma, 1 part would be pi. Okay, we need a hybrid orbital for the sigma. So if you're looking at nitrogen here, you need a hybrid orbital for the single bond, you need a hybrid orbital for the unshared pair, and you need a hybrid orbital for that sigma bond. That would be 3, so we got to go spp, sp2 hybridization. Carbon disulfide. Carbon's got 2 double bonds on it. And then we remember, well, we don't, of the double bond, 1 part sigma, 1 part's pi. So I only need a hybrid orbital for the sigma parts. 1, 2. Sp is sp hybrid orbitals. Carbon monoxide. I could look at the hybridization of the carbon and say, well, there's a unshared pair. I need a hybrid orbital for that. And then of the triple bond, 1 of them is sigma. The other 2 are pi. So I only need a hybrid orbital for the sigma. I need 2 hybrid orbitals. That's sp hybridization. I think I'm going to stop there because you had a worksheet on Friday where you were supposed to go through and do the molecular geometries and the shapes of the molecules. Well, now I want you to go through on that and say, what's the hybridization on the central atom? And I want you to practice that, and I'll be giving you a key to go with it. So I'm going to assign a little bit of reading out of the book also, but I think overall shouldn't be too bad of an assignment. We are getting closer to wrapping up this chapter. This is a much bigger chapter than the last couple we've had, but we still got to talk about polar versus non-polar bonds, but we are looking at a test this week by the end of the week. Okay, you should be studying your ions. This is a tough one right now because I feel it's really important for any chemistry student to learn some of the basic ions. And this is something that I would be, pushing you on here in class, and I'm not quite sure how to push you on it at home. So you got to push yourselves. Study your ions. Take care.